So yeah, I'm going to talk about high energy transients with Prime. I know the main purpose of Prime was to do a microlensing survey, but it's useful to point it at other things as well. And I'm excited, based on the other talks, this is going to be the first picture you've seen where Prime can be visible with the other telescopes there. So it really exists, it's in that spot. So just our primary target of interest is gamma ray bursts. They're the most powerful electromagnetic events in the universe. Electromagnetic output in a few seconds is comparable to the sun's in about 10 billion years. They were discovered in 1967 by the Vela satellites, which were satellites launched to monitor the Earth for, sorry. Yeah, thank you. I just needed to take a deep breath. For nuclear explosions, and they detected stuff right away, and but through triangulation, they were able to tell that these were cosmic in origin. So no one was testing any nuclear weapons. So the progenitors are typically associated with core collapse of massive stars. Long GRBs are associated with powerful type IC supernovae with very little hydrogen present. And also binary mergers, including at least one neutron star. And that was actually confirmed with the simultaneous detection of gravitational wave 1708-17 and GRB 1708-17A. So for Prime, we're mostly interested in afterglows. It's hard to get prompt emission detection from a ground-based telescope, especially at longer wavelengths. Afterglows are just the electromagnetic output after the prompt emission. And afterglows are key to understanding the physics of GRBs. So essentially being able to determine which models make sense, that kind of deal. And also near-infrared measurements are especially useful for high redshift GRBs. All right. So right here's the fireball, like a depiction of the fireball model. So essentially you have a black hole engine and a jet. And the jet allows there to be like this powerful observation. If it was isotropic, we couldn't see nearly as powerful an event, wouldn't be efficient enough. And these are typically observed in the gamma rays, although with Einstein Probe, we've been seeing X-ray bursts as well. Then the afterglows are measured throughout the electromagnetic spectrum. Actually, interestingly, I think they're starting to be able to look for prompt emission in the optical with tests. So more exoplanet and gamma ray overlap there. Prime is good luck for GRBs, as you've already heard. We detected GRB 221009A the day after first light. So this was the brightest GRB of all time. And our observations help show that GRB 221009A is best described by a structured jet. So back to that fireball model there, it's more of a lost the word. Anyway, so it helped determine which model worked best there. And so you can see here, this is on an unprocessed raw frame from our detector that actually had really high noise due to damage from shipping. And we could still see it in a single exposure, just hanging out there. So then we also were able to observe GRB 230307A, which was a bright kilonova detected by Prime a day after detection. The observations helped show that this was the likely progenitor system for this was a lanthanide-rich kilonova despite its long duration. And also this is the first GRB followed up by JWST. So it's a nice shot I got of Prime at night, or twilight. So Prime is particularly useful for this kind of follow-up because it's continuously available for target of opportunity observations when the bulge is not observable. Which is particularly important because you have to follow up GOEs very quickly in order to see the evolution of the signal there. Things are set up so that Prime collaborators are welcome to join in on TOOs that are of mutual interest. This was particularly useful for the potential neutron star black hole merger discovered by LVK, Ligo Virgo KAGRA. It was 240422 ED. It was actually David Buckley emailed us, and Osaka joined us as well in following that up. And also Prime is just one of the few near infrared telescopes in the Southern Hemisphere. So it's a line of sight that a lot of observatories don't have. There aren't many observatories for it. And the wide field of view is actually particularly useful for poor localizations from instruments like Fermi GBM and Ligo Virgo KAGRA. So logistically, we take observations according to an all-sky grid, and whenever possible. We have that mosaic detector, so there's a chip gap there. Sometimes we have to go off the grid, but whenever we can, we do that. And fortunately, anytime we don't have any, Prime doesn't have any targets of interest at that moment. They've been doing an all-sky survey in J-band. That way we can use that for image subtraction later in case we're observing the same field again. So the all-sky survey is covering to about a little over 20 mag AB. And in a year from June 2023 to June 2024, we are able to cover over 7,000 square degrees. This is the coverage map here. So I wrote up some code for a Prime GCN monitor. The GCN is a gamma ray burst coordinates network, actually changed the general coordinates network with all the LIGO data in there. So we have essentially we have a listener that checks to see if alerts are observable by Prime and are of a reasonable parameters to follow up. So basically localization and such. And it automatically generates an observing list to send to the telescope so we can quickly create those. And that's very nice because it seems every time there's an interesting event, I'm not at home. There was a little bit there where I was always at Audi Field watching a soccer match. And had to trigger an event just from my phone, texting people. And then, and it also goes ahead and gives us air mass plots and such. And all that's just sent to our group Slack, so I can just find out right away. We wrote our own data reduction pipeline. Actually, Orion, we pronounce his last name. We have Orion, he's our postback that's been working with us for a little over a year now. He's been very helpful at putting all this together. You can find our pipeline here. And essentially, we just go ahead and take those processed images that Ryusei was just telling us about. And we go ahead and flat field them and do all of our initial astrometry, flat fielding, generate our sky subtraction, and astrometry and stacking. And fortunately, he has some automated script to check the target radius, the localization radius, to see if there's any transients in there. We're working on adding image subtraction and such to improve our ability to find things. Right here, let's see. Yeah, so here's like our plots we use to just kind of get a rough estimate of the limiting magnitude. We essentially determine it right now by just finding the maximum number of stars in 0.1 mag bins. And then assuming that once you're at half that amount, we're at the limiting magnitude. So kind of, up to. So anyway, so with that method, we were able to kind of get an idea of how our pipeline does with different numbers of images. So essentially what we did is we had 1 minute exposures and we stacked those together in order to determine whatever limiting magnitude was for each number of exposures. So this was on a night with about 58% lunar illumination, so kind of a bright night. And in J band, you can see how our limiting magnitude goes with exposure time up to 30 minutes there. And that's in Vega. So we were able to follow up a lot of GRBs. Eventually we got to the point where we could respond quickly. So you see there we have a couple of GRBs way before the rest of them. And that was basically how quickly we could get our pipeline running and take less than a month to get a result out. So we have a number of reported detections there and a number of reported upper limits. And those are basically all gamma ray bursts, except for a few Einstein Probe follow-ups. We also followed up LVK. Well, I just told you that a bit ago. So we were able to cover about 40% of the probability region to 21 mag A, B, and J band. And essentially, we decided to cover a smaller area to a deeper field just to roll out some of the models there. And we had multiple epochs at a 2-day cadence. And then finally, since Prime was designed to do time domain surveys, we thought we'd do a time domain survey. This is still in progress of kind of putting it together. But the plan is to cover larger than 400 square degrees with a 3-day cadence in a couple colors. We're still deciding which colors we prefer to go with. Just that way we can kind of determine the nature of the transient to a depth of more than 19 mag AB. And we chose the fields based on the Fornax clusters, just the convenient cluster to look that's in the southern sky. And then also the Euclid Deep Field Survey fields, since those are also being followed up by Roman. And we've already run a test run this last month, and we're hoping to look through the data and kind of make our final decisions there and see how well we can cover those regions. Any questions?
I would like to jump in with a question if I may. Obviously, in the GRB world, there's other teams that are following these things, and getting on target is super important. How do you then propagate your observations and communicate with the rest of the community? How do you coordinate that?
Oh yeah, so there's the gamma ray general coordinates network. I'll never remember to switch back. Yeah, the GCN. So essentially, anytime we make a detection or have observed the field, we just try to, as quickly as possible, report those findings to the GCN. So basically, you put in really basic information, such as the location and the magnitudes and where you observed it.
Have you considered also telling the map where, because it maps out the spatial extent of where you covered as well?
Oh, so that was for LVK. That is what we did.
Ah, okay.
I can't go back.
I remember the map.
Yeah. Okay. So this is actually from Treasure Map. I did a screenshot of that. So it was nice that I didn't have to generate that myself.
Absolutely, yes. Oh, that's excellent. Thank you.
Yeah.
Any other questions? Okay, you were first.
Have you observed any fast optical transients at pulse? Because I think some models predict they should emit after no emission in effect.
Nope. Yeah, I haven't followed up any of those. I think with another telescope I've worked on, LDT, Lowell Discovery Telescope, we've followed up some of those ZTF candidates there, but it's been a little while.
Do you have any selection criteria on which gamma bursts you follow up in your list of detections versus upper limits? Your range of detections is quite high, given that many bursts don't have counterpart, don't have afterglow detections.
Yeah, so that table maybe was a little misleading. Those are the reported non-detections. For a while there, it was difficult for us to determine what our upper limits were and get that stuff going. But basically for a while there, while we were trying to get everything functioning, we just pointed at anything. Was the selection criteria. I think we're going more towards going for bright bursts and such now that more observers are going to be using the telescope type.
But if I was going to weigh in on that, PTF had a fairly long program of following up on bright GBM bursts. Something that we all learned from 170817 is that the gravitational wave counterpart was a weak gamma ray burst that had a very detectable follow-up. So we should be cautious about picking follow-up criteria because it can lie you and exclude some of the most exciting events.
Yeah, no, the selection bias is a real issue there.